Oh, and I totally killed it. Okay, never mind. So, a reminder. Now the person that I'm talking about all the time is actually in the room, so we can do this thing. Tomorrow at 11 a.m. In front of the Raadhuis, this person, come on stage maybe, we'll be waiting for you for a tour. So, if you're interested in a non-factual tour of Vienna, he's very factual. Yeah, very factual tour apparently.
I'm very good at tours.
That's. I can actually vouch for that. Yeah, okay. So, now skedoodle. Tomorrow at 11. Raadhuis. If you don't know where the Raadhuis is, ask us later. So, next up is Kerstin. She is a developer at Shopify in Canada. She is transforming a massive Rails code base into a more modular monolith. And before moving to Canada, she ran the Hamburg Ruby user group and a local Rails Girls chapter. So, Kerstin. Yeah.
Thank you. So I hope you're not going to be too disappointed. I'm not going to talk about transforming our massive code base. Sorry for that. So when a new user signs up for any kind of web application, the application creates an account for them, but usually it also sends some kind of welcome email. And sending emails is slow. The user should not have to wait for that email to be sent. They should be able to use the service right away. And luckily, sending welcome emails is not essential for account creation. So the application can return to the user right after creating the account and send the welcome email later, outside of the main request-response cycle, by offloading it into a background job. And background jobs are great for monolithic applications, but they're not that useful in a distributed architecture. So today I'm going to talk about how to choose the right tool for workload distribution in different architectures. And I'm going to start with background jobs, how they work, the features they provide, and also some of the challenges they might pose, and when to choose them. And I'm also going to tell you how Shopify uses background jobs to scale one of the largest Rails applications in existence. I'm going to compare background jobs to message-oriented middleware like RabbitMQ. And I'm briefly touching on event logs like Kafka, and how they are different from more traditional messaging, before summarizing the comparison of the three technologies. So let's start with background jobs. In the Ruby world, Rescue and Sidekick are pretty popular background job backends, but there's also delayed job and some others. And the background job is a unit of work to be done in the future. The application server can fork a worker process for running the job, and it shouldn't have to wait for the job to finish. The worker, on the other hand, should be able to communicate any errors. So we need some kind of asynchronous communication between our two processes. We can facilitate that by placing a message queue in between them. Sender and receiver of messages can interact with the queue at different times. And the message is the job, the task to be done by the worker, which is why the queue is often also called a task queue. The application server doesn't have to wait for the worker to process the message. It drops the message into the queue and it can immediately move on, for example, to serve the user-facing request. We can set up more than one worker in order to work on more than one task at the same time. So a background job backend basically is a task queue along with some so-called broker code for routing messages and managing the workers. And it encapsulates the asynchronous communication between our processes, which allows us to keep our own background job code very simple, because our background jobs, our background job classes are not aware of this code being run asynchronously in the future. Let's have a look at background job features. Background jobs allow us to decouple the user-facing request from any kind of backend task and in particular, if those tasks are time-consuming, this helps us to improve the response times and provide a better user experience. If the application experiences a sudden spike, for example, in image uploads, that's not going to hurt performance if the actual image processing is done as a background job. The queue might grow, but the queue is a buffer between application server and worker. And the speed of queuing more jobs is not constrained by the speed of processing them. So the users can still upload more images as fast as usual. If we're facing a very large task, we can split it up into multiple subtasks and queue them as individual background jobs. When we set up more than one worker, they can work on those subtasks in parallel. But our code is again very, very simple because our background jobs are not aware of being run in parallel. All this code needs to know is how to handle one of these subtasks at a time. If a worker encounters any kind of error running a job, the job can be requeued and retried again later. At Shopify, we have some background jobs that are very closely related to the buyer's checkout. And those jobs are certainly more urgent than, for example, firing webhooks. Backends like Rescue and Sidekick allow us to prioritize jobs by having multiple named queues. And jobs queued into a high priority queue are processed first. But if this queue is empty, our workers will not idle and waste resources. They are going to work on lower priority jobs. The main application powering Shopify queues tens of thousands of jobs per second. So we rely heavily on background jobs and the features they provide. The background jobs encapsulate the asynchronous communication between the two processes, but they cannot change the fact that we're dealing with asynchronous communication. And that is posing some challenges. If a job succeeds, the worker confirms that it is safe to remove this job from the message queue. But what do we do if the job is not confirmed? We can allow another worker to pick up that job, but we might end up running our job twice in case the first worker did not crash and is just a little bit slow. On the other hand, if we do not allow a second worker to pick up the unconfirmed job, there is a risk that our job is not running at all in case the first worker actually did crash. So we need to choose between at least and at most once delivery. At most once delivery sounds like a great choice if running the job twice is worse than not running it at all. But usually that points to a flaw in the code. For example, the background job might charge some customer, and we totally want to avoid charging the customer twice. So we're tempted to use at most once delivery. But a better approach might be to carefully track all the charges we are making and make sure that the background job code is checking this state before making any kind of charge. This is making our job idempotent. Running it a second time is not going to create a second charge. And it allows us to opt for at least once delivery safely. Our jobs are leaving the queue in a predefined order, but that does not necessarily mean they are processed in this order. We never know which worker is faster if we have more than one. And also, if a job encounters an error, it is requeued and retried again later. So our jobs might run out of order. And if the order of job matters, then we should not queue all of them right away, because there is a risk of them running in the wrong order. But the first job, after doing its task, can queue the second job as a follow-up, making sure that they are going to run sequentially. A background job does not have to be as fast as a user-facing request. But long-running jobs can create some problems. For example, if you're using Rescue, it is preventing the worker from being shut down while a job is running. So this worker cannot be deployed. And it is also not very cloud-friendly. In a cloud infrastructure, we cannot rely on the same resources being around for many hours in a row. Sidekick is doing a little bit better. If a worker shutdown is requested, Sidekick aborts a running job and requeues it. But even that is not necessarily good enough. The job may actually be aborted again before finishing. So if you're deploying faster than the job can run, this job is never going to succeed. And with a core of Shopify deploying about 60 times a day, this is not a theoretical possibility, but a real issue that we need to address. So Sidekick would not solve this problem for us. But many long-running jobs are actually iterating over a large collection of data. And we split those jobs up into the collection to iterate over and the task to be done. We're setting a checkpoint after each iteration and requeue the job. This makes our jobs interruptible with automatic resuming, and it allows us to shut down our workers anytime we like, so that we can deploy them, and we also have cloud-friendly workers. It also helps with disaster prevention. For example, if our database is experiencing any problems, we can throttle the job or back it off completely, preventing it from making any ongoing incident worse or causing one in the first place. It's also great for data integrity. If we need to move data around between different database shards, we can interrupt the job in order to do so safely. You can reach some of these results by splitting the job into smaller subtasks and queuing them independently. But that makes it pretty hard to track retries and failures for the overall task. A resume is not a retry. By encapsulating these scaling issues into a separate abstraction layer, we are able to keep our concrete background job classes very, very simple because they are not aware of any of these scaling issues. This abstraction layer was recently open sourced, so if you would like to take a closer look, you can find it on GitHub. When should you choose background jobs? The background job backend code is a Ruby gem. It's running on both application server and worker. And the task put into our task queue is an instance of a job class. It's a Ruby object. An application server and worker both need to understand this object. They need to implement that class. And that makes background jobs a great fit for a monolithic application, where application server and worker are running instances of the same code base. The background job backend facilitates communication between different processes. If our background job, for example, is doing image processing, and we would like to extract that into a separate service, we would need communication not between processes, but between services. And this is something background jobs are not that great at. So to summarize background jobs, their great features are mostly based on task queues, and they abstract away the fact that the jobs are running asynchronously in the future or in parallel, which allows us to keep our jobs very simple. But the overall system might be a little bit more complex. We have to watch out for delivery and order guarantees, for example. And background jobs work great in monolithic architectures. Message-oriented middleware is different. It facilitates communication between different services. A very widely used implementation is RabbitMQ, and protocols spoken by message-oriented middleware include AMQP and MQTT, but there is some others as well. This kind of middleware is also working based on task queues. But the logic for message routing and managing workers is now inside the middleware, completely separate from our own code base, from our services. Producer and consumer of messages only need to speak the middleware's protocol. And instead of passing Ruby objects around, they agree on a purely data-based interface. For example, a JSON payload with certain attributes. Since the middleware is based on task queues, it's bringing the features background jobs provide to a distributed architecture. But they're doing more. By placing a data-based interface between our services, we are effectively decoupling them, making it pretty easy to replace a service with a different implementation later on. If the middleware uses a wire-level protocol like AMQP, we are also gaining interoperability, and we can glue together services that are based on totally different technologies. Background jobs mostly are commands. Send this email, process this image, fire this webhook. And we can use command messages for a similar purpose in a distributed architecture. For example, send a message to some image processing service, ordering it to process a particular image. But we can also send event messages, where the producer of the message doesn't know or care what the consumer is doing with the information it receives. And a common use case for that is propagating updates. Let's take a look at this made-up example of a distributed architecture. If my business partner goes out of business, I'm going to update their record in the business partner service. But I also want to cancel their pending orders and put their support contracts on hold. So some client services need to know about this update. It is also common in a distributed architecture that a service needs to work with data that it doesn't own. And to avoid the overhead of requesting this data over and over again, the service might keep a local copy. That also means the service needs to learn about any updates to this data to do a proper cache invalidation. A very common approach for propagating updates is to fire webhooks or make REST requests. But if a client service is temporarily down, it's going to miss a request and it's never going to learn about the update. It also means we need separate requests for every client service, since HTTP is routing one-to-one. And if we're adding a new service, we need to make an additional request. So the service firing the webhooks needs to be aware of all the client services. Instead of using HTTP for propagating updates, we can use our middleware and send a message about the update. And if the message consumer is temporarily down, the message is going to stay in the message queue until it's back. And no information is getting lost over this temporary downtime. Messaging middleware usually is not a single point-to-point queue. It is a topic. And you can picture that as every consumer having its own message queues, and the middleware being smart enough to duplicate the messages into the right queues. So we're no longer restricted to one-to-one routing, and the topic is giving us publish-subscribe capabilities. A new service can subscribe itself to the messages it's interested in by creating its own queues, and the message producer doesn't have to know anything about it. The consumers stay anonymous. We can also add a new message producer, which can start sending messages without the consumer being aware of the new producer. If every service reports some suspicious activities to a centralized fraud score tracker by sending a message, the tracker itself does not need to know anything about the other services. Message producers stay anonymous. Similar to background jobs, we are facing some challenges due to the asynchronicity of the communication. Our messages are a data-based interface, and sooner or later we need to make some breaking changes to that interface. That is really hard to coordinate if the message is routed from multiple producers to multiple consumers, which is why end-to-end routing of messages, even though it's technically possible, is usually not a great idea. Also, the domain, the business logic, is usually represented much better by having multiple different messages, some going N-to-1, others going 1-to-N, instead of having this one huge message covering everything. Messages are kept in the queue if they're not consumed. And that's a great feature if the consumer is temporarily down. But if the consumer is gone for good, messages are piling up in the queue up to the point that the whole broker can get into trouble. So a well-behaved system should make sure that it removes all the queues that are no longer needed. As with background jobs, we usually have no guaranteed exactly once delivery, and writing idempotent message consumers allows us to choose at least once delivery safely. Also, my messages might be processed out of order. So again, if the order matters, I should not queue them all at once, but have the first message after doing the task at hand, queue the next message as a follow-up. When it comes to propagating updates, we need to watch out for the possibility of multiple updates to the same data within a short time frame. So the last message we receive is not necessarily the one from the most recent update. There are two different approaches to propagating updates with event messages. And one is sometimes referred to as event-carried state transfer. In this case, the payload of the message contains the updated data. The service receiving the message doesn't have to make any request to the service owning the message, but we need to include some information that allows the consumer to figure out the correct order of events without relying on the order of messages. That can be a simple timestamp, but the messages might be processed out of order, so we cannot rely on the order alone. A different approach is to send very simple event notifications where the payload is only the ID of the resource that has changed. These messages are commutative, the order doesn't matter at all. But the message consumer has to make a follow-up request to fetch the recent changes. It also means that the consumer doesn't learn every intermediate state of the resource. It only learns the state at the time of the follow-up request. So this approach does not work very well if the consumer is building some kind of history or a timeline. Messages are removed from the queue after processing, so I cannot replay the stream of messages. Replayability is a feature that's very useful when building event-sourced systems. In an event-sourced system, I am not storing the current state of the resource. I'm storing a log of events that I can replay in order to recalculate the current state. If I want to do this based on my messaging system, the message consumer needs to persist the messages it's processing to make sure I can replay them. But that also means every consumer builds its own event log. So there is no single source of truth, and my consumers might end up living in different realities. Message-oriented middleware is a better fit for a distributed architecture than background jobs because it's actually built for communication between services. But it works best with a mostly stateful architecture, not such a great fit for the event sourcing. So to summarize, the features of message-oriented middleware are based on queues and topics, and the topics abstract away the complexity of publish-subscribe, while the queues abstract away the fact that messages are processed asynchronously in the future or in parallel. That allows us to write very simple, concrete message consumers, but again, our overall system might become a bit more complex. Think about delivery and order guarantees. And this kind of messaging is a great fit for stateful distributed architectures. Event logs, also known as commit logs, have a totally different approach to events. And the most famous one around right now is probably Kafka. An event log persists the sequence of events into an append-only log, and the consumers can read from that log whenever they want and as often as they want. The broker itself is stateless. There is no queues. The broker does not track consumption. It's up to the consumer to know where to continue reading the log. Kafka has topics for publish-subscribe, but these topics are not based on queues. Since a broker keeps all events around anyways, it doesn't care if a consumer disappears. There is no queue that could overflow and bring the broker into trouble. And a stateless broker is a very fast broker, giving us high-throughput data streaming, which is great for real-time applications. And this is particularly true for Kafka, which has a really amazing throughput. We're also gaining replayability. Events are not removed after processing, so the consumer can replay them as often as it wants. And all consumers share the same log, so we get a single source of truth if we want to do event sourcing. So this makes event logs a great fit for event sourcing, but also for real-time applications. To sum it up, background jobs are based on queues, and their abstraction allows us to write very simple, concrete job classes, and they're a great fit for monolithic architecture. Message-oriented middleware is based on topics and queues, and its abstraction allows us to write very simple message consumers, which is stateless as far as messages are concerned. And they're a great fit for a distributed architecture if it's a mostly stateful one. Event logs do not use queues. They have a shared log, shared by all consumers. But the consumers are stateful. They need to know where to continue reading that log. And event logs are a great fit for event sourcing and real-time applications. The Thanksgiving weekend, also known as Black Friday, Cyber Monday, is the largest shopping weekend in the US. And in 2017, Shopify built a Kafka-powered dashboard that visualizes in real time how Shopify merchants made sales for over $1 billion over this one long weekend. Black Friday, Cyber Monday 2018 is expected to be even bigger. And if you would like to help us take these things to the next level, come and talk to me after. We're hiring. Thank you so much.
It is break time, and I want you all back here at 4:30 for the next talk. Use the photo booth.